Hello, everyone, and thank you for attending today's webinar, Piles for Miles, Optimizing Pile Design for Efficient Solar PV Projects. I'm Billy Lute, Senior Editor with Solar Power World. Now, before we get started, there are a few things you should know. This webinar will be sent to all registrants so you can view it again. Slides are available to view at any time via the resource window on your screen. You can submit any questions related to today's webinar in the Q&A window. We will try to answer these during the webcast. If we don't get to your question, our presenter may reach out to you after the broadcast. And finally, if you're watching this on demand, you can still use all of these features. Thank you to PV Farm for sponsoring today's presentation. Today's speaker is Maksim Markevich, Head of Technology at PV Farm, and I'm going to turn things over to Maksim.
Thank you, Billy. Thanks for having me here, guys. Appreciate the opportunity to talk about piles for miles. So hey, everybody. Today we're going to talk about piles and optimizing pile design for efficient solar PV projects. And namely, we're going to talk about the importance of piles and potential problems, like piles quite often being overlooked during the early phases of the projects. Then we'll discuss the factors shaping piles. Then I'll tell you a little bit of story, how we actually embedded piles into layout design in PV Farm. And then we'll probably, if we'll have time, we'll jump into product and we'll see just a small piles journey for one particular project. Okay, so let's start it. So the first one, we're gonna talk about the piles in general and about their importance, okay? So let's start with the role of piles in the solar PV system. There are, I would say, a few key players, or maybe a few key planets that decides if your project will be successful, right? So if you will succeed with the project, and the piles are actually part of the capital cost crew, and they hanging out there with two other bros, earthwork and racking. So together they are three pillars holding up your budget. So these bros, they don't work solo, they're always a team. So want to save on grading, it might cost you in piles. Storage on piles, you can go easy on grading. The trick is keeping them balanced and connected. And basically the key is to understand the trade-offs you have, right? So let's go and see a very quick example of hidden costs in the solar PV system. So you can see here like it seems like two layouts. Those two layouts, they are, let's try to spot the differences during the bidding phase, right? So it looks like they have the same DC, they have the same modules, the same trackers, the same number of inverters, the same number of blocks. Everything looks quite identical, right? But if you will check the cost, we'll actually see that there is a 10 millions difference. And this is the full project cost, and 10 millions, quite a lot. So why is that happening, right? So let's diving into the costs. You can see here on the slide like the total project cost, but at the same time you can see the cost broken down for racking, cut fill, and piles. You can see that the first layout has 11 millions more expensive grading, but only 1 million less expensive piles, leaving a 10 million gap. And basically with the same racking cost, it's clear that the civil and the pile bros, they went plain nice in the first layout. Right? Let's zoom in and let's see what's happening further. So you can see that the first layout, it actually had 2.5 million cubic yards of cut and fill, and compared to 1.5 cubic yards in the second, while using 7.5 million pounds of steel versus 7.8 million pounds of steel in the second one. So these aren't small shifts, right? They add up to big dollars. And it's not a zero-sum game for the bros, right? When one cost spikes, it doesn't mean that other balance out. So let's discuss a little bit. So why is this happening? And the point is here is that if you will go back and check this layout, you can see that those costs, they are not actually hidden. It's just they just usually people start considering those costs much later in the process. And so let's talk a little bit about the process itself. Okay, so as you can see here, we have a project development, we have a detailed design and construction, and then we have O&M phase, right? So during the bidding phase, it's a it's a short kind of 30-day window. It might be more, it might be less. The teams, they make decisions that shape the year-long design and construction, and basically 30-year long O&M phase, right? So you can see here that this is the place, 30 days, where many decisions made, right? The cost assumptions and all this stuff. And then you can see the place here where the actually people, they start considering piles, right? Addressing pile designs, factoring geotechnical data, structural requirements, and cost. So, so why is that the piles being overlooked early in the project planning, and then the people start working on them later, right? This issue, it often comes down to a lack of time. So it's not a huge window where you can actually do a proper analysis of the piles. And but lack of time at the end of the day, it leads to a lack of data and lack of tools, right? So teams might not have enough time to gather detailed data or involve structural and civil engineers properly. And the teams often shifts the focus to, I would say, flashier big ticket items. Like even though like 10 million difference in the example earlier is far from insignificant, right? So basically there is no I would say lack of data, right? Lack of tools, and this all adds to this problem, and so the piles being considered properly later in the process. But there is a hope, right? Because piles, they fall into known unknown category, right? So everybody know that there will be piles. So and everybody kind of people understand that they are critical. It's difficult to analyze them early in the process. So if we will talk about the data problem, yeah, indeed right. There is no data at this stage. But if we speculate a little bit about publicly available sources and stuff, you can get some data, right? And so having some data is always better than having no data, unless this data is corrupted or faked or whatever. So there is some data. You can always get like 10 by 10 meters grid surface, download it for your project, and you will have some data. But then there are not many kind of tools that can help you to do a pile design during this phase, because it's a time-consuming process. And if basically, I would say the key here is to actually leveraging the tools that enable faster and smarter analysis, and to ensure that the piles get attention a little bit early in this process. So let's just discuss a little bit how to reveal the hidden factors sooner. Okay, so I would say simple answer to this: use smarter tools to teleport in the future, or at least borrow wisdom from the past. And then that way you can spot problems, or at least like understand the impact much earlier in the process. But obviously we cannot teleport in the future, right? So let's just briefly discuss like how the let's say single axis tracking system evolves during the project. If we will say that there are basically 4 major stages for each project, right? So development, engineering, procurement, and construction. So during development stage, tracker is being represented in electrical way, right? So you have a module count, you have a strings number, and you have an approximate tracker length. So at this stage, you usually don't even know what your tracker length will be, right? So this is the development phase. At the next phase, which is in engineering, it's about mechanical and structural details, about gaps, motor placement, piles. And at this stage, like folks usually understand the exact tracker lengths, and this is the perfect place where layout can be adjusted because of that, right? So then on procurement stage, basically the trackers completely finalized, because the cost needs to be known, right? And the pile lengths and cross sections, everything is defined for construction and being ordered for construction, right? So this is, I would say, this is basically the evolution of the tracker representation, and why we're starting with tracker, because piles usually come with tracker, right? So imagine having this procurement level details early in the process, or again, it might be some future insights, it might be some experience, that because people know, people that build solar farms, they know a little bit about, and they talk to manufacturers, so this information is available. So again, having those details a bit early in the process would definitely help to reveal hidden factors sooner, right? So that's the kind of small insight here. So if we'll go to the next section of this presentation, we're going to talk about factors that shape in piles, right? So, and we will do it in quite in a simple manner. And we will start, and usually like we say that there are actually three major categories of factors that shape pile design. Those include basically underground, on the ground, and above ground, right? So we have a wind, which create a lot for the trackers for the piles, and basically it affects the piles design, right? Then there are factors on the ground, which is essentially high water levels, score, velocity, right? And also things like grading window, tolerance, and many other considerations. And there are also things underground, which is geology and like factors that affect the piles embedment. So in a nutshell, all those, especially things underground and on the ground, they affect, I would say, the pile length, right? And then the things above ground, which is wind, affects the load on the pile, right? And knowing this, knowing length, knowing the anchoring length of the pile, structural engineers, they can calculate cross sections and basically define the piles in a way so they will serve their mission properly. So let's just go into details and talk a little bit about those specifics one by one. Okay. So the first factor is a piles and grading window. And again, essentially, grading window is when your terrain fluctuates, you also have like water flooding areas. You have a high water levels, like half feet, 1 feet, quarter feet, etc. So all those components, they actually define the grading window, and essentially they define the difference between minimum pile reveal and maximum pile reveal. So the grading window adds to the length of your pile, the minimum and maximum, which seen above the ground, right? So and again, just a little bit of this. It looks like the grading window concept is pretty much known well in industry, but we usually consider grading window as max reveal minus minimum reveal, right? And then in the there are many considerations that can be included in the grading window. So first of all, and probably the most impactful one, is a maximum flood depth, right? But there also might be subcontractor tolerance or score depth, or maybe some top accuracy tolerance, or some mechanical installation tolerance, right? All those things, they stack together and they basically create the total grading window, and then essentially it affects the pile length. Okay, so let's go to the next one, and here we're going to talk about piles and water. So we like to think about this in a way when you have your site boundaries, your site, and then you have a different I would say areas with different flood depths, for example, right? And so this flood depths, it affects your minimum pile reveal, because you don't want there is a safety margin, but you also don't want your module to be close to water at any given point, at the point of maximum rotation, right? This is what affects the minimum pile reveal. And the illustration you see here, it basically shows that you see here that you can see 5 feet, 6 feet, 7 feet reveal based on the high water level, right? So if we will go and talk about piles and soil, it's basically a similar situation, which is happening under the ground. So we might have a different soil conditions. It might be like a weak soil or like strong soil or whatever, like types of soil, right? So, but they essentially affect how long, how deep you need to actually anchor your pile in order to make sure that it holds the tracker and the modules, right? So that's pretty simple here, right? So let's go to the next slide, and we'll talk a little bit about piles and grading. We kind of took here a bit of extreme cases, like 0 feet grading window and 3 feet grading window. And you can see that on the left example, we have 6 million cubic yards of dirt versus 4.1 on the right? Because we increased grading window, so we needed to grade the existing grade less, right? And then the piles weight, however, it goes up simply because the grading window is higher. So basically the minimum, maximum pile reveal will be higher. So that's why essentially you see like 6.5 million pounds on the left versus 7.6 on the right. So that's how the gradient affects piles. And let's talk quickly about the wind situation. So piles and wind, right? So in order to analyze, do a proper structural analysis, you need to calculate the load, you need to define the pile types, you need to define the tracker types, but essentially it's all about how those trackers are exposed to the wind, right? So typically manufacturers, they have different types of trackers. And again, this is kind of proxy or the way to simplify things. But basically you might have like exterior and interior, or maybe exterior, interior, and edge, or maybe even more different types of trackers based on how they are exposed to the wind. So why it is important for piles? Because those trackers, they have a different wind load, and because they have a different wind load, they might have a different cross sections of the piles. I would say even more, some manufacturers, they might have like different amount of piles, different number of piles for the same trackers, but with a different load. Let's say you have a exterior tracker, like 11 piles, and then interior, the same tracker, the same number of modules, everything the same, but it's going to have like 10 piles. So one pile less, right? So that's how the wind impact the piles in trackers, right? So let's jump to the next quite popular and I would say trendy topic at this moment. It's piles and racking. So because racking affects piles as well. And the quite popular, I would say, case to consider here is a rigid versus terrain following trackers, right? So you can see on the left, it's a rigid tracker, meaning that it doesn't bend. It's basically a straight line. And you can see the cost, racking, cut, fill, and piles. And then on the right, you can see the terrain following tracker. And you also can see the cost there, right? And usually like people in an industry, they present terrain following trackers in a way like, okay, we saved like that much dirt, or we saved that many millions in cut and fill, right? But there are other aspects. For example, terrain following trackers, typically they're more expensive, right? And then piles, and again, in our experience from the projects we've been involved, typically piles go down slightly because you have this flexibility on the tracker, so you can actually achieve some efficiency in terms of piles, but that's not necessarily the case. Even sometimes there might be the opposite situation, and it's a very project specific, so we cannot say for sure, basically. And that's why we provide examples here, because examples show us that in this particular case, while you can see that like cut and fill savings are huge, right? Like 10, 11 millions, amazing, right? But when you start analyzing the holistic picture, you can see that the actual savings goes down to 1.5 millions because the racking is more expensive here. And basically we need to analyze all those components together. And essentially, that's how the racking affects the piles. And again, we see those three bros here, cut, fill, piles, and racking, and those things it's hard to actually separate and to consider independently. Okay, so that's about factors that shape the pile design, right? So now we go to the next section where we will talk about piles in PV farm and how we actually build it. We're gonna talk a little bit more about principles we tried to follow and we were taking into account while developing the piles into PV farm. And those principles, they will basically touch gradient as well and some other components very related to piles. So let's start with the first one, which is called cumulative optimization. So the way we build PV farm, our software, is that we allow our customers to perform multiple runs on a single surface, right? Using different gradient strategies. And under gradient strategy here, we understand all the restrictions, not only regarding the slopes of the piles and of the terrain, but also minimum, maximum pile reveal, gradient window, and then is it rigid, is it terrain following, what's the bay-to-bay slope change, what's the cumulative slope. So there are basically many parameters. But what's important is that you can see on the right scheme here that again, the site usually is broken down into high water level, normal water level, low water level, right? And then moderate, strong, weak soil. And based on those insights, we can actually apply it. We can apply a completely different grading strategy. This is, I would say, this is so-called horizontal stacking direction, right? So we grab a terrain and we stack different grading strategies in a horizontal direction, and then, but also there is a vertical stacking direction, and this is more related when when you have like an area with trackers, and you need to run different grading strategies for rods, for skids, for trackers, and for the couch grading, right? So in that case, you might be in a situation where you will adjust existing grade for trackers to get the final grade, but then you will need to also to start doing kind of additional analysis on top of final grade, but for the rods. So then the optimization will start stacking in the kind of vertical direction. Okay, so let's go to the next one. And this is actually was probably the most important principle, because we were aware that trackers have been represented in a electrical, mechanical, and structural ways, right? And like I would say the detailed representation of tracker contains all the definitions of everything, right? Not only electrical like modules and strings, but also like all the gaps and all the piles positions, and moreover, like pile positions based on the wind load of this tracker. So there are many things to input when you create a tracker. So the way we wanted to build it is that we wanted the right details to be available at the right moment. So you don't need to insert them from the beginning. You can actually insert like piles information late in the process. We'll talk about it more in the next slides, but now let's jump to the next one, and we'll talk slightly about advanced configurability. Again, before we started building piles and grading optimizations, we talked to many manufacturers, and there are plenty of different systems with quite a unique behavior, right? So when we talk about rigid and terrain following trackers, kind of everybody understands it, right? But there are some examples where trackers might bend on a certain piles. So not everywhere, but for a certain piles. Let's say on a motor pile, or maybe on some other piles, or maybe even we'll have a different bay-to-bay slope changes, right? So we wanted to think about this a little bit upfront, just to have this unique opportunity to support such systems. So the next one is more like a bit kind of mathematical standpoint of view, but again, when we were optimizing, like we actually didn't separate terrain following and rigid trackers, and the reason for that, if you can optimize for terrain following, basically optimizing rigid ones is simply a matter of adding additional constraints, right? So yeah, that's it basically. You just add additional constraints, and your optimization works in the same way, but for different tracker types. And such approach allows us to think about sophisticated, like restrictions like cumulative slope, for example, right? We can support the constraint called cumulative slope when your tracker shouldn't accumulate a certain slope change to the right and to the left from the motor. So and many more others. So this approach helped us to actually support such things. Okay. Yeah, non-destructive flow. Fancy words here, but the thing is that I remember when we started building PV Farm, we actually were thinking about having like a central catalog with like all possible equipment configurations, and then we were imagining that the people will just reuse, right? But as reality explained to us, we sometimes there are some changes which needs to be done, later in the process, and those changes shouldn't necessarily affect the actual global configuration of the tracker, and this is why we build the I would say project specific level of editing, so you can again add details or change details and re-optimize grading just at the project level, instead of like going and changing the equipment itself and then using this equipment when generating layout. So yeah, and then another thing and another I would say consideration we took into account is that two-step optimization. We actually separated optimizing for piles and optimizing for grading, because those are basically separate optimizations and they can be run independently. So sometimes you basically just have a final grade, or maybe you have existing grade and you don't want to do any grading, but you still want to have a solution which will have the most efficient piles, right, in terms of lengths. And so this is why you probably would run just a piles optimization. And I want to explain what it means. So in terms of piles optimization, imagine like you have a track, you have a, let's say, terrain, and this is a bit an extreme case. I just wanted to show the way, on an extreme case, then it's clear how it's going to work on any other case. So the way is that basically usually you have, let's say, terrain, and you're not allowed to do any grading there, right? And then you have a tracker slope limitations. And essentially, you can actually place this tracker on the terrain in a way which will minimize the total length of piles if you have a minimum reveal and minimum embedment requirements, as well as the maximum slope along axis. Or maybe not necessarily the maximum slope along axis, but like maximum slope along the bay, and then slope change bay to bay, and then cumulative slope change. Again, it's a game of constraints, so we basically add more constraints and we optimize for piles. So that's what piles optimization. And then when we do cut fill optimization, we basically we can run the cut fill optimization together with piles optimization. So we can start mixing those things, and we can run them independently or sequentially. So let's go to the next principle. This is actually a juicy one. And this is the problem we wanted to solve, is that when you design stuff, right, you can see on this picture, you just apply like constraints for a tracker, right? Slope along axis, slope change, piles constraints. And then as a result, on a design, you basically have hundreds of different types of piles, not only by cross-section, but also by lengths. And what's happening on the procurement stage is that procurement engineers, they do binning, basically. They start, sometimes it's a procurement engineer, sometimes it's a mixed structural procurement engineer, but basically they start creating like less classes of piles, because for the sake of being the project being more easy buildable, right? So, and when we started building piles, the thing we wanted to build as well is actually procurement design feedback loop. So basically, after you do binning, and here I just basically added a little bit of longer pile just for the sake of visualization, but essentially you can apply your binning classes back to the project, and in that way, in that way you kind of have the updated your informational model, and the data is always up to date. And whenever you decide to take a CSV or any other deliverable output, you basically have it up to date. So that's a quite useful feedback loop. So then let's talk about wind load exposure analysis slightly. So the way we build it is that we don't. So first of all, we don't do like a structural engineering of piles, but we build trackers, for example. They are intelligent objects, so they know about wind, right? So we have a separate solver which defines the wind load position of those trackers, and then those trackers, they have a bunch of different pile configurations, and those might vary as well based on the wind position. So we also have intelligent piles that know about wind. And so if we will add intelligent human to this equation, who knows about piles design, based on this information and based on the binning classes and lengths of the piles, including reveal and embedment, so the intelligent human can come up with a right cross sections and update our defaults in terms of cross sections. Again, some kind of simplification. So and I just want to refer back to this, to the slide where we talked about 30 days window. And so the point of such simplifications is basically to get a little bit more useful information a little bit early in the process, right? So we are not trying to solve pile design here like completely, but we're trying to, to get a bit more data, which will help us to manage risks better and to make a better decisions, right? So, well, we'll jump in back to the slide where we stopped. And if we will go further, this is my favorite one, because we actually struggled a lot with the meaningful optimization, so-called. And what it means is that actually, when building a meaningful optimization, you basically want to have a results from your algorithms similar to real life results. You don't want to have crazy efficient, like, I don't know, 1/10 of feet by 1/10 of feet grid cut fill optimization, which is only possible to achieve if you will send people with shovels there. So that's why we tried to build it in a way, and that's what we validated 100 times in a way that makes sense. And what it means basically is that let's say when you bring a terrain data, it has a certain grid size. Let's say one by one, right? 1 by 1 feet or 1 by 1 meter, right? And then when we run grading, we actually convert this grid into kind of grading grid, and we kind of I would say enlarge it a little bit. And the whole point of this enlargement is to actually mimic grader machine blade behavior, because we know that basically the grading will be happening with the machine, and it has certain blade size. So basically we enlarge the grid to run the efficient cut fill analysis. After that, we check in if we need to add so-called virtual piles. And so we add in virtual piles if the base size in between piles is basically bigger than the grid size for the cut fill optimization, and it helps us to avoid bumps in between piles, right? So it helps us to actually optimize the terrain on the trackers. So your basically the distance you put there from the module to the final grade is always basically satisfied. And after that, we also do some analysis to provide a daylight slope, to provide a connection from the graded area to the kind of existing grade area. And that's what we call a meaningful optimization. And this is a tough part, basically, especially working with the different stakeholders, like on the construction side, on the design side. They all think a little bit differently, and that's why this one, that's why it's called meaningful. So the next one, again, essentially, when we were building the piles, we wanted to link to have the kind of central model, single source of truth, and basically all the deliverables being linked to that model. So you can always find a specific pile and explore what's happening there. Why we got this lens, why we got this cross section, what kind of beam class for this pile, etc. Right? And let's go to the next one, which is about multi-surface support. Most of our clients, and when we were working with them, they use multiple surfaces in terms of not necessarily like an existing grade as a multiple surfaces, but more like high water level surface, for example. So what we came up with, we knew that this is how it works, and so we wanted to actually to give this option to upload, let's say, high water level surface, like here, right? And so then we needed to define the context impact, and this is where we create, let's call them gradient influence areas. This is like the areas, let's say, in terms of high water level example, it's like 1 feet depth, half feet depth, etc. Right? And so then by having this, the first principle I mentioned, which is about cumulative optimization, we can actually use those gradient influence areas and run different gradient strategies when converting existing grade into final grade. So that's what we actually call a multi-surface support. And also, if we will go further, I just want to talk briefly about a couple of simple insights in terms of basically what other insights we got by working with those tools with our clients current. And just want to share one particular here about how people evaluate existing grade. And again, this is a bit of an extreme example. This project is our demo project, and it has very crazy terrain. So it's like slopey and like very huge slopes in there. And so like the way how it's done usually is that people try to avoid, let's say, high slopes on the terrain. So you can see here those red and blue areas. This is the areas where, let's say, the slopes of the terrain higher than 10%. Okay, and so those slopes as well can be converted in some kind of helpful boundaries, and those boundaries might be made as an exclusion areas, and then when making layout, we just generate a layout avoiding those exclusion areas. So for this particular project, we just got 123.9 megawatts DC. So as you can see here, there are lots of like gray spots where we didn't place any trackers. But when we build this pile things, we actually realized that there is a more, I would say, conservative way to evaluate existing grade. And this way is about evaluating existing grade by piles. So what's happening here is that instead of avoiding areas where the terrain has like high slopes, we can actually place trackers on that terrain, optimizing for piles, but then avoiding those trackers that have at least one pile with reveal longer than expected. So let's say your minimum maximum reveal like 5 feet, and then you add some error of margin, and then basically if you have the piles with reveals longer, so you expect that, but you will need to do gradient there if you want to place this equipment, right? And so for this particular project, DC total was 16.2. So it's a 123 versus 16.2. It's crazy. So, but again, it's a demo fancy project, and but essentially what I'm saying here is that having some information about piles might help. If we again go back to that slide, just real quickly, to do a little bit more conservative assumption at this stage, looking a little bit in the future, having like default piles, not necessarily exact piles, and then evaluating terrain, I think it's going to help to actually manage risks in terms of like having data is better than no having data, right? Okay, so coming back where we started. So now we're going to talk a little bit about piles journey, and probably here I will do something that I wouldn't recommend doing. So we're going to do a quick demo of how PV Farm looks like and how we work with piles basically in there. So I'm going to share my screen, and we'll go through just a simple workflow, how we actually support piles in PV Farm. Okay, let me share my screen. Here we go. Okay, I hope you see PV Farm. Let me hide everything else. So here's our starting point. Let's say we have a simple layout, just flat at this stage, okay? So we have a trackers there. Those trackers, they are configured in a way that they have a lot of useful information, but also they are exact copy of the real trackers, okay? So if I select my tracker and will open its pile positions, you'll see that the tracker has a fancy configurations of different wind load variations. And then basically each one of those wind load variations, it has a different pile configuration, okay? So let's remember this for a second. Then we have a terrain, and even before placing trackers on the terrain, and by having those wind load positions, we can actually run a quick analysis, which is basically wind load positions. So we can update wind load positions and we can control kind of exposure parameters. So lateral wind exposure, medial wind exposure, etc. And so then, we can just quickly check what kind of trackers we have in the project. So we can see here interior, exterior, edge, etc. Right? So we have this information, which basically goes further and affects the piles, right? So now, let's say we want to see what's going to happen with our reveals, and I will open basically on the right reveals. We basically will search for piles, and let's say I will just do piles length, or whatever information we need here, and we don't have reveal yet. Let's just quickly go in terrain and piles, and I will not do any cut fill for now, but I will run the for all my trackers, basically pile optimization, and this is a very fancy site. This is why we will see a lot of interesting trackers here. I'll show you for a second what I mean. You see, like, for example, here, so this is quite a sloppy situation, but because we don't do any gradient, we just basically place a tracker in a way to support this slope along axis as one constraint, and then another constraint is embedment should be minimum 7 feet, and then the reveal should be minimum 5 feet. And basically, based on those assumptions, from exactly what I showed you in the presentation, we placed those trackers on the terrain, right? And so then if we will go further, and let me just show you the pile reveals, this is where we can actually colorize our trackers. If, let's say, you can see here, the 10, 20, 30, this is the actual pile reveals, right? So you can see here, and you can quickly validate where do you have problems, in terms of, like, let's say if you have one single pile longer than 675, then you will consider this as you will need to do grading, right? And you can like try a different approach. For example, what if we're gonna do terrain following tracker, with very aggressive conditions, 25% slope change bay to bay, and then cumulative slope. I actually will show you this. So you will start getting like like a shorter piles, but you would still see the tracker behavior. So it's cool, it's quick and interactive, so you can run it like and check it real quickly. So for example, if we would allow just a little bit more slope change along axis, we would see that our trackers would adjust it real quickly. And you see that the piles, basically the more flexibility you allow for your terrain following trackers, the more efficient piles you got, right? So you can see here that we don't have any more 30 feet reveals, so our piles maximum 12 feet, but obviously this is a pretty crazy terrain following tracker. Then let's, for example, run quickly a gradient just to make sure that our piles are normal and we can see the cut fill volume, right? So what I'm gonna do, and I actually will run it with more or less okay numbers. So we will allow 15 percentages for the tracker. We will make it a rigid tracker, and we will do 15 percentages north-south, like a slopes, 15 percentages east-west slopes, 1 feet gradient window. We will set net balance to 0, meaning the amount of cut will be equal to fill, and we'll basically run the cut and fill analysis. And so what's going to happen, and let me hide this annotations, is that you can see that our piles became much shorter, and we can actually do one quick thing, because here, when we were running this, we were expected to have like a shorter piles, like maximum should be 6, but I run it on a very drafty calculation precision. So I'll basically increase the precision here, and I'll run this analysis one more time just to have a better results. It might take a couple of seconds, but it's still pretty quick. So, so now you can see that all of our trackers, they don't have pile reveal longer than 6. We have some error margin, but basically they are installed, placed here, right? And if we will get closer, we can quickly check our cut and fill situation. Basically, like the red is cut, blue is fill. So you can see that and we can quickly make it like 3 ranges, make it black and white. You can see the amount of cut, the amount of fill. You can see the share, the percentage, and all the stuff. Or if we will decide, let's say, to not consider certain depths of the soil as a cut and fill, we can start actually changing this in here. So Those are all interactive and simple, right? And so also what's really fun about it here is that we can always like grab the specific tracker. Let's say this is how it's installed. We have all the parameters, all the information, but also we can like switch to, okay, what did we have before? Okay, this is our the existing grade. This is our final grade, right? And we can see if we will select this tracker one more time, we will see all the information about, like basically embedment, reveal for each pile, cross sections, etc. Like you can see the slope changes and quickly see the difference. For example, if we would decide to actually try terrain following trackers instead of rigid trackers, we would basically go back to our like existing grade, so no cut fill now. So we have a terrain as we uploaded here, and then I'll just add more or less okay, slope changes. Let's say we'll do slope change bay to bay as a 3%, and we will add cumulative. Let's say we don't have any restrictions for cumulative slope. I'll add it as 100%. So what's going to happen is that we will start seeing, and again, we run it in a high precision. So we'll start seeing like the trackers, they start bending and they start basically kind of going like a serpentine, right? And you can see it here. And again, essentially the same story, right? So you have the tracker as an intelligent object. And then if I go here, you will see like a lot of information in terms of, okay, what's my cumulative slope first to last? Meaning from first pile to the last pile, like what's my, like where is this tracker is facing? Is it north facing, south facing? Or, like maybe like what's my cumulative slopes to the left and right wing? And like what's my, like slope first to last pile, et cetera, et cetera. And what's important is that all those parameters from those trackers, they've been available for you to actually to review and analyze on a level where you can like colorize them in many different ways. So for example, I can simply, search for facing. I can just quickly check, okay, this is how many trackers I have south facing, this is how many I have north facing, right? Or maybe I wanna go and check some position, and again, wind load position, or maybe max bay to bay slope change. Again, colorizing them, seeing this difference, etc., etc. And then we're gonna start having some fun because we can actually see that we have also the pile markups. So I'll just isolate it quickly. And so we will start seeing that we have piles, elevations, top of elevations, right? And if I go quickly into piles, into pile reveal bins, this is the perfect place where we can start binning those piles, okay? So the way it works is that basically you define the bin and, you will get a bunch of piles moved into this bin. And I'll just switch to a different tracker type and I can do the same story here again and again. And you can see that as soon as those piles, they arrived in some bin class, you can see that they being colorized. You can see the rows, you can see the pile positions itself, and basically you can download this quickly into CSV file and work with this further. Okay, I'm coming back. Stop sharing my screen. I think it's I spent a bit more time, but the last time we've been asked to show some product, so that's here it is. Yeah, I think that's all I have. Let's go to Q questions, basically, and let's talk a little bit about what questions you have, guys. I really appreciate your attention. So, do you have any questions?
Yeah, looks like we've got a handful of questions. I know there are many of you in the audience, and we've only got till the top of the hour to answer questions, so get those in now. First up, we have, how does PV Farms Piles design stand out from other competitors?
Mm-hmm. Okay, that's I would say that's my favorite question. Okay, so couple of things. First of all, advanced optimization. So we can really do quickly things with piles, optimizing for piles, optimizing for grading, combinations of those things. Then the second one, interactive design flow. I hope you saw how quickly you can actually go and check different grading strategies, different limitations of manufacturer. So it's quite interactive, and also you can see those fancy charts, and you can like see changes real time, which basically allows you to quick iterations and quick what-if analysis. And the one thing I didn't show you, but we have also adaptive cost model, which basically links piles, earthwork, and racking. So you also constantly get a feedback on what does your project cost, basically. Yeah, so that I would say this is our 4 differences from competitors. Yeah.
Got it. And next up, how can I get access to try PV Farm?
Oh, guys, just reach out. Go to pvfarm.io. Just there is a button, book a call or something like that. Reach out. We will discuss, and then we'll provide access. We'll start trial. So just reach out to us.
Okay, awesome. And what are the limitations of PV Farm in terms of project size?
I would say in terms of terrain and surface size, it's 120 square kilometers, so 30,000 acres. So in terms of projects, if it's a layout only, meaning the trackers arrays, it's up to 2 gigawatt. If it's a layout and civil, it's up to 1 gigawatt. And then if it's a layout, civil, and electrical engineering, it's up to 700 megawatts DC. Yeah, I know those numbers out of my memory because many questions about those. Yeah.
Got it. Okay, and had one here and I just lost it. Okay, does PV Farm have the ability to export pvsyst.pvc files or AutoCAD DWG files? Sorry, that was a lot.
Yeah, that's a great question. We cannot do the PVC, meaning like a PVCist project file, but we can do export into SSD shading file for PVCist. And in terms of AutoCAD, we can export into DXF, and we can export layout, we can export pile point plan, we can also export low voltage, medium voltage, so pretty much everything into DXF basically.
Awesome. And at which project stage is PV Farm being used and by whom?
Oh, okay. I would say we have like a very mixed user base in terms we have manufacturers that use PV Farm for quotation process. We have EPC contractors that use PV Farm for basically design 10%, design all the way to design 30%. So we have engineering consultancies, and we also have developers that have engineering teams on board. They also use PV Farm. So I would say pretty much all stakeholders that actually need to produce layouts and that need to actually do some kind of I would say some good level of details for civil engineering and electrical engineering.
Understood. Does PV Farm have the ability to generate SLDs?
Yes, we do. We generate SLD in the product, but also when we export the DXF file, we have SLDs included in that file in AutoCAD. Basically, you also will be able to open SLD, and we do it on a block level. So let's say if you have a project, 100 blocks, you'll get 100 pages in your DXF with different SLDs for those blocks.
Understood. And there's an acronym in here I don't know, so bear with me here.
Okay.
Are there plans to calculate generic TOPLs for foundations based on tracker and location?
Okay. Yeah. Generic TOPLs, you said, right?
Yeah.
So absolutely, and I think if I understand correctly, because I'm also not sure what's generic, what generic says here, but basically we calculate. I will just explain what we calculate because I think this is the answer to this question. So we, when we represent the tracker, we have a torque tube, and then the pile connects into the torque tube, and basically we provide currently the deliverable as CSV file, which contains all the top of piles elevations. And when we calculate top of pile, we calculate it in the middle of the torque tube. We don't include pile bearings. We give you this coordinate basically, and this is already available. Yeah.
Got it. All right. Next up, what is the best way to get tracker configurations?
Oh, um, I would say it depends. Um, it depends what's needed, but I would start from electrical configuration, modules, number of modules, number of strings. Then I would go and check the lens, whether it's satisfying for me or not. If not, I would start tweaking gaps, motor gaps, module gaps, and overhangs and stuff like that until I achieve the required length of the tracker. And only after that, I would start working with piles. And sometimes you need to do piles a little bit, at least you need to have the exact number of piles before you start working with piles, because it will affect your tracker length. But basically, essentially electrical configuration, then mechanical configuration, and then structural or piles configuration at the end. That's how I would recommend. And this is not, yeah, we want this to make this process easier than it is at the moment, but yeah, it is possible. That's the most important part.
Okay. And someone had a question about is is PV Farm available to the public, or is this strictly like a commercial software or service?
I would say at the moment it's a commercial software, and yeah, I mean we are talking with students, and obviously happy to help with and provide free access for students and educational purposes, right? But it's a strictly commercial software.
All right. Okay, we're getting a bunch in. Let's see if anything's marked. Okay, we got one here. This is a bit of a long one. You might want to take a look at it too. Number 36 under the Q&A.
Okay.
What kind of pile analysis does PV Farm use? And then they've asked quite a bit there.
Mm-hmm. L pile. Yeah. No, it's not. It's we for us it's basically if it's we just use like we solve an optimization problem. So we I would say L pile is a bit no, I'll not comment because I'm not sure. But basically, what we do is that we solve the optimization problem, and we use integer programming. And basically, when we try to define how to actually place the tracker with its own restrictions on the terrain, we actually find the best position of the tracker based on the constraints we have to get the minimum total length of piles. So we get the sum of all lenses of piles, and then we place it on the terrain in a way so we minimize this number. Yeah.
Understood.
Yeah, that's
okay.
a good question. I would, yeah, that's a great question, actually. Mm-hmm. Cool.
Okay, and next up, there is a cyclic process between the electrical and the civil side. How does it work? I think is what they're trying to ask.
Yeah, I got that. That's actually a cool question. So essentially, when we were building PV Farm, we actually wanted to combine multiple areas of expertise or multiple disciplines together, and so we were trying to build a product in a way that it supports those feedback loops. Let's say when you have layout and you want to understand how expensive this block in terms of civil grading, you can just go and run the civil analysis for this block only and get an answer. Or or basically you go the same, you get this block and you generate low voltage wire, and also answering the question how expensive electrical part would be. So we support those feedback loops. They are not perfect, but because we want them to be more interactive, but we definitely support those disciplines together. That's a good question. I would like to talk about it more. Yeah.
All right. Yeah, speaking of, that's all the time we have today. If you have additional unanswered questions, please feel free to contact our presenter on your own. This webinar will be shared with all registrants so you can view it again at your convenience. I'd like to thank Maksim for being here and doing today's presentation, and of course PV Farm for sponsoring today's webinar. And thank you to everyone in our audience for participating. You sent in a bunch of questions. Thank you for that. I hope you enjoyed our presentation, and we invite you to join us for more Solar Power World webinars in the future. Thanks, everyone.
Thank you, guys. Bye-bye.